welcome you all to this second lecture session of Applied Thermodynamics. In the previous class, we had discussed about it was an introduction class where we had discussed about the fundamentals of thermodynamics. How, what are the tools or what are the parameters by which by the help of those tools, we tend to describe thermodynamics, like the states, the properties, like the paths, like the processes, the thermodynamic cycle. We had a discussion on those things. Today we shall continue on this. You may consider this as a continuation class, and today we shall be discussing about thermodynamic equilibrium, and thereafter we shall discuss about the concept of temperature, the zeroth law of thermodynamics, and then we shall discuss about what do we mean by quasi-static process. So let us start today's session. So uh, there is a bit of uh, recap recapitulation here. So if you remember, in the first lecture we had discussed it is always required at least we always require at least two independent properties to specify a state. Okay, so this information is little bit incomplete here. So to complete it, we'll be discussing Gibbs phase rule. So in your school level physics, you have known Gibbs. You have studied about Gibbs free energy and all. How does a chemical reaction happen? What are the energy considerations? So that is Gibbs for you, and this rule will be very important to understand. So as you can see here, a formula is given to you. So the derivation of this formula is beyond the scope of the syllabus, so we are just concentrating on the formula here, or the Gibbs phase rule. So see, number of independent intensive properties required, number of components minus number of phases plus 2. Now see, so what I said earlier was that to specify a state, we need at least two independent properties. So that was a specific case. Okay, and this is the general rule. So we can write this I P. Okay, so it is independent intensive properties is equal to C minus P plus 2. Okay, so uh, let us consider the number of components is 1. That means a gas is present in an in a piston cylinder arrangement. Okay, so gas is our system, so it is a single component, and the phase is also 1. So C becomes 1, P, that is phase, also becomes 1. So we find that IP, that is the number of independent intensive properties. So in my previous information, that word intensive was missing. So this is a kind of addition. You must consider it here. So when C is equal to 1 and P is equal to 1, IP becomes 2. Okay. So now my information can be seen as a concrete one. It will be complete now. So for a single component, single phase system, the number of independent intensive properties which are required to specify the state, it will be 2. Okay, now let us consider the number of component remains 1, but the number of phases goes on changing. Like if we consider a mixture of water and water vapor, that is steam. So if we consider a mixture of water and steam, then we can obviously understand uh, two different phases, liquid and gas, they are coexisting. So the number of phases become two, and the number of independent properties becomes it becomes 1. So whenever the number of phases are increased, you see that the number of intensive properties required to specify that state becomes less. Or this can be mathematically defined also, but the point is, for the water steam mixture, we know the boiling point of water is 100 degrees Celsius. That means when we have this information, the boiling point of water is 100 degrees Celsius, we can get other informations about that specific state. So the temperature, the boiling temperature or the boiling point of water is 100 degrees Celsius. So this is enough for us. From this information, we can calculate all the other properties. Okay. Now what happens if uh, this these phases, the number of phases becomes 3? So we are considering a single component system here. Okay, so the number of components is not changing. It may vary, but the situation will become much more complex. Okay, physically it will be very complex. So the number of what will be, it will be 0. So that means it is already a predefined state. That means we are considering the triple point of water. That means water, that is liquid, ice, that is solid, and vapor or gas. They are coexisting. Okay, so at triple point, water, ice, and steam, solid, liquid, and gas, they are coexisting. So this is the triple point where you don't require any other specific state to to calculate all the other properties. That means there is no requirement of properties here because it is already predefined. This triple point is a specific case, is a predefined state. Okay, so this is why we don't require any other information here. Now why it becomes important? uh, for any system to understand the states, to understand the characteristics of that system, we need to know what are the properties, and these properties needs to be mentioned for the total system. It it should be, suppose I am mentioning the temperature of water is 35 degrees Celsius. That means the total water which is present in that space, the total water has 35 degrees Celsius. So this is an very important information. Okay. Now what happens if there is some difference? So let us I'm just what happens if there is difference within the mm, mm, so let us consider a solid metallic rod over here, and here you have just placed a source. What kind of source? It is a heating source. That means heat starts to flow within this solid rod. So obviously you will find the temperature is T1 here and it is T2. So you will obviously understand that this T1 will be greater than T2. So within a certain system there is the temperature difference. So within a certain system a temperature difference is present. So from this understanding, so there may be certain cases where temperature difference may be present within the system itself. Along with along with this information, it is quite obvious that the temperature difference between system and the surroundings are present naturally. So this difference in the properties can be present in both ways. So it can be within the system and it can be between system and surroundings also. So this understanding is very necessary because we are going to move on to the equilibrium portion. When we will be moving on to the equilibrium portion, this understanding is very much required. So from the uh, information of Gibbs phase rule, we we have understood when the number of components is 1 and the number of phases is also 1, then the number of independent intensive properties required are 2. So we'll be studying this case where the number of components. So we'll be studying the thermodynamics of single component, single phase systems. And sometimes we'll be also studying the thermodynamics of single component, two phase systems. Okay, so let us move on to the next thing. So now, uh, before going on to this, we shall move on to this concept of thermodynamic equilibrium. Okay. Mm, so, okay. Sorry. Mm, we'll be going on to thermodynamic equilibrium. So just I mentioned earlier, I have just mentioned it earlier. So the difference in properties of the systems can be present within the system itself and it can be between the system and the surroundings. Now what happens if we isolate this system from the surroundings? So that means a system and a surrounding, the surroundings respect to that system were interacting with themselves. Interaction means there was some energy transfer going on. Energy in terms of heat, in terms of work, or whatever may be. Okay, so that means whenever there is some kind of interaction going on, the property values, it can be intensive or it can be extensive. So both the property values goes on continuously changing. Now what happens if we isolate them from the surroundings? So there is no chance of interaction now. So when we isolate the system from the surroundings, when suppose suppose so this is system A and this is system B. Some kind of interaction was going on. Now what happened? You just differentiated these two. Now, so this is an, let us consider this as an uh, adiabatic wall. Okay, adiabatic means no heat can penetrate, and we um, also ensure that there is no provision of other kind of energy transfers except than heat. So we have already provided an adiabatic wall which ensures that there can't be any kind of heat flow available, and we also ensure that there is no energy transfer available here. Now what happens? Let us consider uh, let us consider it had property values of PA, PB. We are taking two different property values because we are taking a single component, single phased system. Okay, so when we isolate this system from the surroundings, obviously after some time we'll realize that these property values will reach to some different values, and it should be understood that the this PC and PD values are the values of equilibrium. That means when I had isolated this system A from the surroundings B, there may be some kind of imbalance present within the system. So we give some time, this imbalance uh, goes outwards. That means after some time there is no kind of uh, there is uh, there is no imbalance present in this system. So that means the system is going on to an equilibrium state. Now this state is called as dead state. Okay, so this state is called as dead state. Okay, so means uh, dead state means there is uh, there is an equilibrium present within the system. Okay, uh, so this is the point of view of um internal equilibrium when we are isolating it from the surroundings. So if 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 we create a system which will not permit any kind of, say, we have created a system, it is kind of an isolated system, so it has to be an isolated system, because I'm just mentioning why I am saying that it has to be an isolated system. So if a system doesn't permit any kind of energy interactions, that means, and so isolated system is the only example where no energy transfer or mass transfer is allowed. That means the properties of the system within the system itself are in equilibrium, and they will remain in equilibrium always. Okay, so either it has to be an isolated system uh, which doesn't permit any kind of interaction with the surroundings, and the system the state of the system has to remain in a dead state. So referring to these points, we can say that the system will remain in thermodynamic equilibrium. Now this thermodynamic equilibrium can be achieved uh, from three different perspectives. The first one is the thermal equilibrium, which is mentioned here. Okay, so I'm just writing in it here. So thermal equilibrium. Then it is mechanical equilibrium. Mechanical equilibrium. And the second one and the third one is chemical equilibrium. So when there is three kind of equilibrium present within the system, we can say that the whole system is in thermodynamic equilibrium. So we shall be discussing more and more about these specific cases, that is the thermal equilibrium. What do we mean by thermal equilibrium? What do we mean by mechanical equilibrium? What do we mean by mechanical equilibrium. What do you mean by chemical equilibrium? Okay, so let us start with the thermal equilibrium. Okay. So just give me some time. Okay. So to explain about thermal equilibrium, we need to understand here comes the importance of Zeroth law of thermodynamics, and the concept of temperature is also evolved from this thermodynamic equilibrium, or specifically thermal equilibrium conditions. Now let us consider just give me some time to draw here. Okay, so let us consider this one as system A. Okay, and this one as system B. Now this system A and system B are differentiated by an adiabatic wall. Okay, so these two systems are differentiated from themselves by the help of an adiabatic adiabatic sorry, just give me some time. Just adiabatic wall. So I have already mentioned that this adiabatic wall means it doesn't permit any kind of heat transfer. Okay, now let us consider these same two systems are interacting with themselves by when there is an diathermic wall present between them. So in the first case we had an adiabatic wall, and in the second case we are having a diathermic wall. So diathermic wall means it allows to transfer heat from A to B or any kind of system. So let us consider this one as a metallic wall. So obviously we know metals are good conductors of heat. So this is what? This is diathermic. I hope you are able to understand the spelling here. Diathermic wall. So diathermic means it allows to transfer heat from one system to another. So what is the difference here? If there is an adiabatic wall present, these two systems can't interact with themselves. So that means if we consider some properties xa and xb, sorry, just it would be better if I write xa and ya. and here I write x b y b for the sake of your understanding. So these two properties are not going to change because they are differentiated by an adiabatic wall. So it doesn't allow any kind of energy transfer, specifically heat transfer. So these properties are not going to change. But whenever I am providing an diathermic wall, these properties will obviously change. These properties will obviously change. Okay, so I hope this is quite understandable to you. So let us consider a specific case here. Again, we'll be using some diagrams. Okay, so okay, so let us consider this system A and system B. They are separated by an adiabatic wall. Okay, so there is no exchange of energy within A and B, but they are interchanging energy with an separate system, which is system C. So let us consider here, and so this is diathermic and this one is adiabatic. So adiabatic wall and this one is diathermic wall. Okay, so what will happen? So both the systems will obviously interact with C, and after some time we will understand this system and this system will reach an equilibrium state. Okay, similar things will happen for system B and system C. So let us consider the properties which change after they had attained the equilibrium state is the properties are mm, xc and yc. So this is the value after attaining the equilibrium state. Now if if so both the systems A and B, they have attained the same value. Okay, and even if you place, and so let us just remove this wall. So we are removing the adiabatic wall here, and we are placing, sorry, very sorry, so we are placing, and we are placing a diathermic wall. So just to remind you that both the systems A and B, they have attained an certain equilibrium condition with C. Okay, so this is the case here. Now it is quite easily understandable to you that as both the systems has the same exact properties, they are in thermodynamic equilibrium. They are in thermal equilibrium with each other. Okay, is it understandable? I think that means, so in the first case, you have separated the systems A and B with an adiabatic wall. So they don't interact with themselves. Now you place a third system with a diathermic wall which allows heat and other energy transfers so that the individual systems A and B can reach equilibrium conditions with system C. So we are talking about thermal equilibrium here. Okay, so you know the conditions of thermal equilibrium. So and then when both the systems A and B have reached equilibrium conditions, and even if you separate them or place a diathermic wall between themselves, there will be no change of the properties because they have reached the equilibrium. They have the same values exactly that of the equilibrium conditions. So there is no chance of uh, change in the values of in the property values. Okay, so this is the condition when thermal equilibrium is reached. Okay, so we can define these thermal equilibrium conditions as the equilibrium states achieved by two or more systems, which is obviously characterized by restricted values of the thermodynamic properties of the system after they have been in communication with each other through a diathermic wall. Okay, so from that aspect we can define zeroth law of thermodynamics, so which I had just explained. It is written in words. When a body A is in thermal equilibrium with a body B and also separately with a body C, then B and C will be equilibrium with each other. So here in the diagram earlier I had just mentioned A is in equilibrium with C, B is in thermal equilibrium with C. So that means A and B will be also in thermal equilibrium with each other. So this is very simple and this is school level things. Now from this aspect, from this understanding, we need to define what is temperature. So uh, all of us know that temperature is the property by virtue of which heat flows from a high temperature body or a hotter body to a cooler body. Okay, so temperature is the property by virtue of which heat can flow, or from the microscopic point of view, from the point of view of statistical thermodynamics, we can say that it is the average kinetic energy of the molecules, right? But from the perspective of thermodynamic equilibrium, temperature can be also defined separately. So which is given here. Temperature of a system is a property that determines whether or not a system is in thermal equilibrium with other system. So this becomes very important. The concept of thermal equilibrium becomes very much important to define the case of temperature. Okay, so I hope you have understood all these things. So we were primarily discussing about thermodynamic equilibrium. We had mentioned there will be three separate cases: mechanical equilibrium, chemical equilibrium, and thermal equilibrium. So in case of thermal equilibrium, we can say that there will be no temperature difference. So dt, if dt refers to the change in temperature. So this dt should be 0. This dt needs to be 0 to maintain thermal equilibrium conditions. And for the next part, suppose we need to discuss about mechanical equilibrium. So mechanical equilibrium. So the same logic. If there is no difference in pressure within the system itself, and if there is no pressure difference between the system and surroundings, then we can say that the system itself, the system and the surroundings are in mechanical equilibrium. That means we can say dP, or the difference in pressure, is equal to 0. Okay, so this is important here. That means if there is some kind of pressure difference, then there is an opportunity to obtain some kind of work. We can extract some kind of work whenever there is a pressure difference. Okay, uh, so if if the properties of the system within the system itself and the properties of system and the surroundings are in mechanical equilibrium, that means no work can be extracted. That so mechanical equilibrium condition means there is no chance of extracting work from the system. Okay, so it also means that there shouldn't be any kind of pressure difference. Just like in case of thermal equilibrium, there shouldn't be any kind of temperature difference. And what do we mean by chemical chemical equilibrium? Chemical equilibrium means it suggests that there should not be any kind of difference in mass concentration present. Okay, so there shouldn't be any kind of difference in mass concentrations of the system and the surroundings present. So that means there shouldn't be any kind of mass concentration differences present in the system itself. So this is the things I am just saying more and more time, so that you can be accustomed with these things. You can be accustomed with the thermodynamic equilibrium criterions. Okay, so we can also refer uh, to write d mu or dc equal to 0. So that means there is no possibility of chemical reactions happening within the system and the surroundings whenever there is no difference present in the mass concentrations. There is no chance of any kind of chemical reaction happening between the system and the surroundings. No mass transfer is also possible here. So if we collaborate these uh, three conditions, it becomes, we can write dt equal to 0 and dc equal to 0. So that means this is the case from which we can understand. So if these three equilibrium conditions are perfectly maintained, then only we can say the whole system is in thermodynamic equilibrium condition. But to inform you, to tell you that in practical cases, when we extract some kind of work from these interactions, we must inform you that practically no system doesn't remain in the thermodynamic equilibrium conditions, because if thermodynamic equilibrium conditions are maintained, then there is no possibility we can extract any kind of work from it. So this has to be remembered. Practically, no system remains in the thermodynamic equilibrium conditions. Okay. So reality obviously differs from the practical case. But for the sake of better understanding, for the sake of analyzing the thermodynamic cases, we assume that each state remains in thermodynamic equilibrium when when the interactions are taking place between the systems and the surroundings. Okay, so this is an important assumption here. So I have just told you, practically no system can be present in thermodynamic equilibrium, but for the sake of thermodynamic analysis, we assume two basic things. The first one was the thermodynamic equilibrium conditions, and the second one, all the thermodynamic processes takes place in quasi-static mode. So this is what we refer as quasi-static processes. Now, what do you mean by the word quasi? Quasi means it. This word quasi means almost. So we are referring to a process which is almost static. Now I'll be just mentioning you how is it possible here. Now see, from the diagram here, let us understand some facts here. So this is this is an this is a frictionless sliding. That means if the gas pressurized, apply some pressure, this sliding will move in the upward direction. Okay, and there is a perfect insulation present here. That means no heat transfer is allowed. Any kind of energy transfer is not allowed here, except the transfer of energy by the gas or the weight. Now, let us assume this person, this child, who is trying to remove this weight. So, if he removes the weight, then obviously by the effect of this pressure, the gas pressure, the piston will move in the forward direction. That has been shown in the diagram. Now what happens if we divide this weight in two single times? So the person here has to remove the two uh, two different weights. So initially, see, here the change was much more rapid. So the change was, suppose the piston moved uh, a distance of h in the upward direction. Here we'll see the piston will move h by 2 distance in in a much longer time, because why? Because there are two weights present, and let us see if there are uh, many number of weights present here. So let us, so here in this diagram, here you can see that this weight has been divided into, so let us consider, say, uh, 15 divisions. So the change observed by this piston will be quite slow. So, the number of divisions in which the weight is divided, so as we increase the number of weights, we will see the change is slow. It becomes slow. So at the finally we will observe the same change, but the time required to for this change will be much more. Now, if this weight is divided in infinite number of equal weights, then the time required for the whole change to the movement of this piston will take infinite time. So we have to understand, when there is an infinite small gradient present between the system and the surroundings, the changes are slow. uh, the changes are so much slow that we refer these individual processes as quasi-static, as almost static. So we just can't observe the changes because the differences. Gradient means difference. Whenever there is some kind of difference present in the system and the surroundings, there is an opportunity to extract some kind of work. Okay, so the difference is so small that the changes observed by the transfer of work is also very small. So collaborating these numerous number of processes, we will ultimately observe the same change, but in an infinite time. So infinite slowness. This is the characteristics of any quasi-static process. So a process where the changes are very slow. The changes observed are very much slow. So that so slow that it can be termed as almost static. Like here you can take an example. Suppose you are dropping the sand molecules one by one. Okay, so after you have poured some kind of sand here, it has to be some amount. If it collects up to a certain amount, then only you can observe the piston is moving in this direction. The piston will be able to apply some kind of pressure. So you have started pouring sand in single grains. Okay, you start with a single grain, then you go on pouring the sand grains one by one. So after a long time period, you will see these sands will be in this kind of shape, and then only this piston can apply some kind of pressure. So if you follow this order, that means you are dropping these sand molecules one by one, and you are observing the changes. So the changes will be so much minimalistic, you can't observe it. After a certain time, when the mass of the sand is kind of you can measure it. Obviously you can measure the small values of sand, but when it is a up to a certain quantity, so that it can so the piston can apply some kind of force, then only you can observe the changes. Okay, suppose like this can be example also. Suppose this is, just let me remove this. um, okay, suppose this is the third floor or the fifth floor where you live, and this is the ground floor. So generally you go to your fifth floor by a lift. So the position change of your movement, the movement is quite rapid when you are using a lift here. But suppose one day your lift there is a breakdown in your lift, then you are compelled to use this staircase. Then what will happen? You will start from here. So each step you take, there is some kind of work involved in it. That is, you are working against the gravity. So in each case you will observe the fatigue. Okay, so this can be also compared with quasi-static process. So okay, so here when you were using the lift, the changes were very much rapid, but when you are using the staircase, the changes. So the changes are very much slow. So this is the difference, primary difference between any kind of quasi-static process and a rapid process. But uh, in practical cases, uh, any kind of process doesn't follow this quasi-static manner. The changes are very much rapid, but for the sake of our analysis, for the sake of continuous plotting of the states, for the sake of generating the thermodynamic curves and thermodynamic paths, we tend all the processes as quasi-static process. Okay, so you have to remember this is absolutely nothing but assumptions. That means there are two basic assumptions here. Any thermodynamic process maintains thermodynamic equilibrium conditions, and you have to remember also that the changes which takes place are taking place in a quasi-static manner, but these are mere assumptions. In reality, all these assumptions doesn't uh, really take place. Okay, we shall be discussing about the reversible process and the irreversible process later on, but just to help you understand, this doesn't apply practically. So I hope that uh, I have introduced the thermodynamics to you. This will be quite enough to understand the thermodynamics, the tools by which we tend to analyze thermodynamics, and that is the parameters. So we had discussed about the parameters, the tools by which we can discuss some thermodynamical conditions, we can analyze the thermodynamical interactions. So this is for today. I hope you have understood all the topics I have gone through. Now, uh, if you face any kind of problem and you have any question, then you can mail me here. Okay, so I'm sorry, I'm just providing my mail ID, or you can comment in the in the video sections of the YouTube, or you can directly mail me. So in the next class, I'll be giving you some assignments regarding this basic understandings of thermodynamics. So thank you for being with me. And so this is how we end our second lecture session. Thank you.